Hello, welcome to the second movie about the Nobel Prize in Chemistry for 1901, won by Johann Henricus van 't Hoff, and we deal with his lecture, his Nobel Prize lecture he held, about osmotic pressure and chemical equilibrium. Well, van 't Hoff starts by underlining that his investigation in question started at least 15 years ago, so that is about 1885, a work that was built upon even earlier work by other investigators. The subject in question, osmotic pressure. The first question to answer, of course, is, what is osmotic pressure? Well, a quote, when a solution, for instance of sugar in water, is separated from the solvent, in this case water, by a membrane which allows water but no sugar to pass through, a so-called semi-permeable membrane, then water forces its way through the membrane into the solution. This process naturally results in greater pressure on that side of the membrane to which the water is penetrating, at the side of the sugar solution. The phenomenon is known since the beginning of the 19th century, but is only seriously investigated since 1880. It was the botanist Pfeffer who first measured the pressure in 1877 by making a membrane which satisfied the following three conditions. It was permeable to water, so water can pass through, but is unpermeable to sugar, sugar cannot pass through, and withstood by no means negligible pressure to which it was subjected. He was unable to find a relation between the value of this pressure and the concentration of the solution, its temperature, etc. Celebrated physicists also failed to find this relation, and the work was forgotten. The vital role played by osmotic pressure in plant and animal life, Hugo de Vries in particular emphasizes its importance to plant life. Such turgor is osmotic pressure must exist in plant cells if they are not to wither. In other words, it is essential for growth. Hugo de Vries found a method of establishing how concentrated a solution must be if it has to have the same osmotic pressure as plant cells, if it is to be isotonic with them, just the same constitution in the cells and in the solution. Here you see a semi-permeable membrane. The blue molecules, the blue balls are water molecules, they can pass through. The red balls are to be sugar molecules, they cannot pass through. So in general, water will go into this reaction. A little bit of water may go the other way, but the majority of the water molecules will move to the solution. And the sugar molecules, they stay here. They cannot pass the membrane. Here you see the same again for red blood cells. Here you see the red blood cells. If the concentration of salts in the blood cells is the same as in the outside, it's called isotonic, and water will go in and water will go out, but there's an equilibrium between them. In a hypertonic situation, the solution outside is more concentrated than the solution inside the blood cell, and most of the water will go out. Hypertonic is the other way around. The concentration in the cells is higher than in the outside, so netto water will go in. Donders and Hamburg then discovered that osmotic pressure plays no less important a role in animal life than in plant life. If the external pressure is too great in relation to the osmotic pressure in the cells, then a remark similar to wilting occurs with animals. And in this respect, it was particularly remarkable that solutions found to be isotonic in this respect were also isotonic for plant cells. Lastly, in chemistry, osmotic pressure is very important because it can be related directly to what is known as chemical affinity. This is illustrated with gypsum, calcium sulfate with water. The calcium sulfate binds with the water in almost the same way as plant cells hold the water inside themselves, and the force with which this takes place can be measured in the same way as de Vries measured the osmotic force of the cells. In the end, Jepson will also wilt and cannot longer hold the water, giving up to the resolution of greater osmotic pressure. You see that again what we saw with the red salts. This is an isotonic solution, so there's no netto water displacement. Here you have a hypertonic situation, so there's netto water going in, and here's a hypertonic situation, netto water is going out of the cells. So much for the earlier work. It was found that with sufficiently dilute solutions, the osmotic pressure was the same as the gas pressure. The pressure which the dissolved substances would exert as a gas. That's remarkable. The pressure that is the result of molecules colliding with the walls is comparable to the pressure that is the result of the dissolved molecules colliding with the semi-permeable membrane. See figures 1 and 2, we see them in a minute. Under the same conditions, the same number of molecules, temperature and volume, the pressures are the same. In other words, the osmotic pressure, that's the little p, is just as great as the gas pressure, big P. Capital P. It was found, however, that a relatively small group of solutions, all of aqueous, of acids, bases and salts, constituted an exception. The pressure was I times greater than that theoretical value. So the osmotic pressure is I times the gas pressure. Yeah. Here we see the figures 1 and 2. Here you have an osmotic solution. Sorry, here you have a gas. The molecules hit the gas, the walls. Here you have an osmotic situation. Here is a semi-permeable membrane inside the solution, and the molecules also hit the walls. For the non-exceptionals, the value is therefore 1. If you have this formula, P is I, P and I is 1, then P is P. Then you have this again. Van 't Hoff then moved on to the subject of equilibrium, chemical equilibrium. A distinction must be made between complete and incomplete reactions. For instance, the explosion of dynamite is a complete reaction, because afterwards there's no dynamite left anymore. The formation of methanol and formic acid into water and metal format is incomplete. All four molecules exist at the same time, 1/3 versus 2/3 in the next example. So 1/3 of the molecules is on the left side and 2/3 of the molecules is on the right side. And that equilibrium can change, of course. In the last example, the reaction works in both ways at the same time. That's called an incomplete reaction. Then the laws governing this chemical equilibrium in the case of dissolved substances can now be deduced by using the basic relationship for osmotic pressure. The first of these is here for non-alcohol electrolytes, just the non-exceptions. The sigma, the sum of n log P is K, and K is the equilibrium constant. And for electrolytes, the same, again, times I. Dus the sum of n times I times the logarithm of P is the K equilibrium constant. Here you got the n is the number of the molecules, I is the exception factor we just saw, P is the osmotic pressure, and K is the equilibrium constant. Then there's a second law, dk dt, that's just the change of the equilibrium constant in time, is a half times V divided by T squared. W here, I said V, that's Dutch, I'm Dutch. W is the quantity of heat formed in the section, and T squared, that is the temperature squared, and that must be the absolute temperature, dus the temperature in Kelvin. Yeah. Finally, the last formula is K is minus half A divided by T. And said that allowance must be made for the quantity of work done during a chemical relation, the quantity being linked with the equilibrium constant. A is the Gibbs energy, and T again is the temperature, and K is again the equilibrium constant. Van Hoff then gives some results obtaining by means by the formula. 1. The molecular weight of dissolved substance is now easy to determine. 15 years ago it was possible to assess the molecular weight of gaseous substances only. By means of osmotic pressure it is now possible to determine the weight of dissolved substances. That's an important feat. In addition, homogeneous mixtures of solid substances are comparable to solutions, and the law of osmosis can therefore be extended to solid substances. That's another feat. The problem of molecular weight determination has to a certain extent been solved. It was quite a big problem in the time. He also states that during condensation and solidifying, molecules as a rule do not lump together in contrast what is often thought. Then 2, equation 2, P is IP, was at first the critical point of the theory. Arrhenius was able to demonstrate the cause of the exception, reducing equation 2 to the equation 1, P is P. Osmotic pressure is gas pressure. Then 3, we need to go further into equation 3, A, the sigma n log P is K. It coincides essentially with the law of mass formulated by the two Norwegians Gulbeck and Waage, except with regard to I and N. Then equation 4, the change of the equilibrium constant in time is half mile the heat W divided to T squared, the temperature in squared. Links a chemical equilibrium constant with K with that of heat W evolved by the reaction. It can be tested experimentally, and it has indeed been confirmed experimentally. The equilibrium at ordinary temperatures has shifted so far in favor of those products that are situated on one side of the arrows in the chemical formula that no trace of the products on the other side can be detected. So an incomplete reaction becomes a complete reaction. But at higher temperature this changed and an equilibrium is reached, so the reaction is then incomplete. This was further investigated by De Ville and De Pree. A corollary to this law shows how the chemical equilibrium varies with the temperature, namely how, as the temperature increases, more of one compound is formed at the expense of the other, or the other way around. Thus as the temperature drops, the reverse situation occurs. This corollary can be stated as follows. At low temperature the greater yield is always of that product whose formation is accompanied by the evolution of heat. Then 5. It is only recently that it has been possible to test this equation, and that is the equation K, the equilibrium constant is minus half times A, that is the free Gibbs free energy, divided by the temperature in Kelvin. Beder and Knupfer have determined that K, dus quantitatively, and also A, which is in my opinion the Gibbs free energy, but it is not clearly stated by Van Hoff, but it has to be. De Vries then concludes by giving an example of further discoveries related to osmotic pressure, both in chemistry and biology, and refers to the work done by Loop. Well, that is the summary of the Nobel Prize lecture of Van Hoff. If you want to read the complete lecture, follow the link. Well, thank you for watching, and maybe I see you next time for the Nobel Prize in Chemistry or Physics or Medicine of 1992 or a later year. Thank you.